Welcome back, astronomers. We're going to be looking at more things to do with stars today in our lecture over chapter 18 in your textbook. So stay tuned and we'll take our Doctor Who police box here off into the far reaches of the universe. If you're a Doctor Who fan, hopefully you get this. If you're not, then Netflix and Prime are your friends. Let me see if I can figure out how to share the screen here. There we go. The stars, a celestial census. So we're going to look at different stars and how these things actually are classified and how we can make sense of what's out there in different ways. There are lots of varieties of stars. We've already talked about that in chapter 17 and before. Some are brighter, some are dimmer, some are hotter, hence the blue stars there. Some are cooler, hence the reddish stars there. This is a cluster in the Small Magellanic Cloud. You may remember I've shown you a couple of pictures that show you the sky from the southern hemisphere. That's one of the galaxies we can see with the naked eye relatively close up to our galaxy, but we can't see it from here in Indiana, not from the skies here, because we never rotate around in this direction. We rotate around in this direction, and it's always down here, so the Earth is always blocking it. Fortunately, we have quite a number of facilities in the southern hemisphere. In particular, there are massive complexes being built in the Atacama Desert of Chile, and have been for quite a while. And Australia has quite a number of good facilities for viewing. And we have some various others around the world as well that can see the entire sky either in combination with things on the opposite side, or they're close enough to the equator that they get a good look. If you could have something situated exactly on the equator, you would be able to really see all of the northern sky and all of the southern sky. The problem is there aren't too many good venues right at the equator to do that. When we're looking at this, we see it's about 200,000 light years away. Remember the Andromeda galaxy, the big spiral that's our closest big spiral, is more than 10 times that distance to us along the way. So because all of these stars are more or less the same distance, I mean, some are here and some are here, but they're far enough away that it's sort of like talking about how far away is Chicago. Well, the south side of Chicago is 50 miles closer to us than the far north side suburbs of Chicago, but we still talk about Chicago as being one distance away from us. And we can talk about these stars as being pretty much equidistant, and therefore they are useful for us figuring out how things might be brighter or dimmer or hotter or cooler along the way when we get that up. This sort of shows an estimate of the different types of spectral stars that we have within our own sort of bubble around the sun. Remember, our sun is a G-type star. We have we don't have any O stars. We don't have any B stars. We only have 2 A stars. So the hottest of the hot stars, we don't have any within our sort of 21 light years. So we're sort of thinking we're here and we go 21 light years out into every direction. There are no O stars and there are no B stars. But notice as we sort of get into smaller and smaller and dimmer stars in our classification here, we get more and more and more stars. That is pretty typical of stellar populations. There are a lot more dimmer stars than there are bright stars along the way. When we're looking at white dwarfs and brown dwarfs, they are in a class somewhat by themselves. One of the issues with brown dwarfs is they are hard to spot. So I would suspect this number here, 33, is low and will probably go up. And one of the things I tend to do at least once a year when I'm looking at a chart like this is that I go back to the NASA website and see how the numbers have gone up. We're probably not going to find any more G stars. We definitely won't find any more A or F stars. We would have seen them by now. But brown dwarfs, we will likely find a couple more on a regular basis. White dwarfs, we may find a few more as well. They're in a class, as I mentioned, by themselves because those are zombie stars. Those are the leftovers after stars have lived their lives. And we'll talk about those in particular a little bit later. I think 2 chapters away from now here. This computer simulation sort of shows where we have the different kinds of stars that are in our neighborhood. When we're looking at the dimmest stars, we typically need to look at infrared. Infrared is lower energy. Infrared are cooler stars. And infrared is not something we can see with the naked eye. So we really didn't have an idea about a lot of these stars until the past half century when we were able to start looking for those. So remember, even though within our sort of 21 light years, we don't have any O stars. There are some O stars in the sky that are really, really bright. Bright does not mean close. Remember how the light falls off at the square of a distance. So if it's 100 times as far away, it's only going to be 1/10,000th of the light that's coming off of it. But sometimes we're still overwhelmed by the brightness, even though it's far away. So that tells us that things are actually pretty bright sometimes out there, but they are enormously far away. So when we're looking at some of the closest stars here, we might think about Alpha Centauri. Alpha Centauri is actually a binary star. We might, in fact, call it a trinary star system because it's actually two stars going around each other with yet another star going around that pair. And we call that third star that's out there Proxima Centauri because right now it's closer to us. It's more proximate to us. It's not always going to be the case. But it's about 4 light years away, give or take. Close is good in astronomy. You'll hear me say that a lot. I'll have bumper stickers made. So one of the things that we see in these different images here, this portion in A, the upper corner here is highlighted here. The light blends together, even with many of our best telescopes. The light tends to merge together if we're looking at it in Roy G. Biv. And Proxima Centauri is actually really dim. It's a spectral type M. Again, if we sort of go back to our chart here, notice the M stars. They are among the dimmer of the stars that are out there. And it's relatively new in terms of our discovery of it, because it's not something that shows up in a naked eye astronomy. When we are looking at the power of light coming off of a star, remember from our last lecture, we talked about the luminosity, that's how much light it's putting out, and the apparent brightness is how much is reaching us and how much we tend to see. Again, if it's a 100-watt bulb, it's always going to be a 100-watt bulb, but if it's way over here, it's going to be a lot dimmer than if it's right up here, and it's going to be a lot brighter to you. So apparent brightness has to do not just with the brightness of the star, but also how far away it is. Luminosity is how bright it is, just in an absolute sense along the way. We talked a little bit about parallax. As we go around the sun on our planet, sometimes we can look at a star, and if a star is nearby against the backdrop of much more distant stars that are out there, it may seem to shift position in just the same way that if you look at something, and I don't know if I've done this experiment with you in this class up till now. I don't think I've done this. If I have, just ignore it. If I have, or do it again. So here's how parallax works. Look around the room. Look somewhere around the room. Look for a poster on the wall, or if you have a window, look outside the window right now and look at something and close one eye. So look at something and close one eye. And now put your thumb over that thing you're looking at with the other eye closed. Now close that eye and open the other one. So you'll see the thing you're looking at jumped. That's because we've got stereoscopic vision. One of the things that happens here is that I could measure the distance between your eyes and the amount of the jump. That's where we get this geometric progression, or geometric drawing simulation here. And we could do the angle and the distance between your eyes and figure out how far away it is. Because all you need to do to figure out the sides of a triangle is the distance of one side and one of the angles. that's there. Well, the distance between our two eyes, if we're looking from the Earth from one part of the year to half the year later, is 2 AUs. An AU is 93 million miles. So 186 million miles between your two eyes. Things should jump. The further away things are, the less they jump. You can try that experiment in your room or outside sometime as well. Focus on something that's closer and it'll jump a lot more. Focus on something that's further away and it doesn't jump nearly as much. Well, most stars don't jump at all, according to this with naked eye parallax, because they're simply so far away that's not going to happen. That was one of the arguments of the ancients against us moving around the sun. They said, well, surely things would be jumping back and forth with parallax. They didn't realize just how large the universe is. When we're looking out there at different stars, the most luminous stars, 10 to the 6th up here, L sun, that's luminosity of the sun. So we take the sun and say, okay, that's 1. And when we're talking 10 to the 6th, we're talking 1 with 6 zeros after it, so 1 million times more luminous than the sun. When we look at the least luminous stars, here we've got the negative here. So we're moving the decimal in the other direction. So we're talking about not 1/10th, not 1/100th, not 1/1000th, but we're getting from 1/1000th to 1/10,000th of the luminosity of the sun. So we're somewhere in the middle. In terms of our sun. We're on the dimmer side, but we're close to the middle in terms of how luminous our sun is, how much energy it's putting out. And here we can see some, just for sort of size comparison, low mass and high mass stars. One of the things to notice, here's Proxima Centauri, which I mentioned before, the close star that's part of the Alpha Centauri, Proxima Centauri system. There. Notice how much smaller it is than the sun. We're talking, it's much closer to Jupiter's size. And I showed you a graphic that showed Jupiter with some brown dwarfs. Proxima Centauri is a red dwarf. It's not a brown dwarf. And we'll talk about what the difference between those two things are later. But it is a very small star. Notice here we've got the sun. It is 10 times the mass. This M sun, this means the mass, how much stuff is in it. Sirius is twice the mass. Now it looks like it's much more than twice the size. And that's where we have to talk about when we're talking about size. Are we talking about mass, how much stuff is in it? Or are we talking about volume, how big is it along the way? Usually when I talk about size, I will be talking about mass. If I'm talking about volume, I will pretty much specify that I'm talking about volume. But really, I'm usually talking about mass. Of course, because Sirius has twice as much mass, it has a hotter engine inside that's pushing out much more than the sun's energy from its engine inside. So therefore, it's actually by volume much more than twice the size of the sun. And then when we get up here to Spica, which is 11 times the mass of the sun in terms of size, that's way bigger than 11 times the size. Because think of these as 3-dimensional. By the time you turn that into a gumball machine, you could fit hundreds of sun-sized gumballs in there. But again, 11 times the mass of the sun gives it a really souped-up engine inside there that's really perking along. One of the things you can notice is the lifetime here. Our sun, 10 to the 10th here, we're talking about 10 billion years. But notice as we get more massive, Sirius only lasts about 1/10 that amount of time. It's only going to last 1 billion years. So the sun will be here for billions and billions of years after Sirius has already gone and exploded. And we'll talk about that later in the semester. Spica here, it's not even going to last 100 million years. If it's lucky, it might just make it to that length. But chances are good it's going to blow itself apart well below that threshold. And the larger the star is, the lower this number goes down. And the bigger the mass, the lower the number. Sometimes they can be so massive that they rip themselves apart before they fully form. Conversely, Proxima Centauri here will be sort of laughing and say, oh, well, I'm so sorry, son, because it's going to last 1 trillion years. It's going to last 100 times longer than our sun. So when our sun gets ready to throw off its excess layers and turn into a red giant and say, nope, we're not doing this anymore, this would be a good time to get into the Elon Musk cars and take off for a planet around Proxima Centauri. Hopefully, we've got several billion years in which we can perfect our technologies, we might actually just be able to do that in that time there. But notice that you get larger here in terms of main sequence stars. That means the engine that's running inside is burning hydrogen into helium. We go from red down here in the cooler to yellow to white to blue. And so that tends to be the progression there. Again, red, lower energy, blue, higher energy. Brown dwarfs, on the other hand, are stars that the engine never quite kicked on. So what they're doing in terms of radiating energy is just sort of the leftover energy from stuff that's falling into it and the pressure that's creating heat, as well as the residual heat of the material that made it. But it never became heavy enough, pushing in with enough pressure for that engine to kick on with the hydrogen turning into helium under high temperatures and pressure. So these are sort of mega planets rather than stars themselves. Proxima Centauri is not a brown dwarf, it's a red dwarf. That's a small star that did have the engine kick on. So notice this is 0.08, so about 8% of the mass of the sun. Notice back here, Proxima Centauri is 12% of the sun. So that's the golden edge right there between 8 and 12. So we say roughly 10%. By the time you get 10% the size of the sun, chances are good you're going to kick on your engine and become a red dwarf and a regular star. Brown dwarfs are proto-stars or failed stars, or because sometimes a proto-star, which is in the process of forming, will eventually get more material and kick on its engine. So, but these are not actually burning a fusion reaction inside. They are infrared, and that's why they're hard to see, because they're not generating light in the Roy G. Biv area the way other stars with the hydrogen fusion are doing. Here again, as we saw in our demographics of stars around our sun, we don't have many large stars for the smaller stars that are out there. Remember, we had 94 M-type stars in our neighborhood. We are one of, I think, 8 or 9 G-type stars in our area there, and we only have a couple of sort of A stars and F stars. We don't have any that are going to be up really in this area here. But think about it in Hollywood. For every Brad Pitt that's out there, we have a couple of people who are stars of television shows. We have a lot more people who are extras, and then a lot more people who are milling around in the background that you never even get to see listed on the Internet Movie Database. That sort of works in a lot of different capacities in life. That works in the universe as well. At the same time, the big stars tend to burn themselves out quite frequently, whereas the smaller stars just stick around forever and ever and ever. So some stars, a lot of stars in fact, are part of stellar systems where they are binary. That means 2 stars going around each other, or trinary. Remember, Alpha Centauri A and B are going around each other, and they have a third one that's going around like this. Sometimes we can see this happening just by watching them. Notice we have A, B here, and we see A is moving, A is moving, A is moving, and then of course B is also tending to move. Then B up here, then A is back, and sort of by 1950, we're back in the same range here. 1960, we're over here again. And so we can tell they're interacting. We have to watch them go in a complete sequence pretty much more than once if it's a visual binary. We can use other methods to confirm whether or not they're truly with each other. But if they could be separated a long way away, but from where we are watching, they seem to interact. But they might just keep going and going and going. It's only after we watch, okay, they're actually related to each other. It would take us 50 years to watch this happen once, and even then we'd want to keep watching to make sure they're not just spiraling around and then going on their own way. So we have to watch for these things, and sometimes it can take quite a long time to view what's happening. So visual binaries are possible. They tend to be fairly rare along the way. Here we can sort of see a system that has been brought up through the Hubble and other ESA processes, we can see starting here in April 2000, we have the different motions of the stars going around each other. And we're sort of looking here, we have one main star, it looks like here, and we have another shifting around as it's going around. So as it says, we have a brown dwarf star and we have an ultra cool L dwarf star. So we do have some very, very low light stars that are here. And one of the things that we see is that they're going around each other. Barely the size of the planet Jupiter, as it says. So when it says that, we're talking about the volume, but the weight, the mass, is 8.5%. Remember, that's just inside that range where it would actually kick on the engine along the way. Most binary stars, most star systems where they're attracted to each other in that way are not equals. They're not equals. So one is going to be larger than the other. When one is larger than the other, it can often look like the smaller one is going around the larger one. But in fact, they're going around a mutually mutually equated or calculated center of mass. So if you had two that were equal in mass, they'd be going around each other equidistantly. If one was twice as much as the other, then the one that's twice as much will still be going around a bit, but the lower mass one goes around a lot more. That in fact happens in our own solar system. The sun isn't just sitting there while everything's going around it. As Jupiter goes around, it actually tugs back and forth on our star. So the sun actually wobbles a bit in response to the planets going around it too. This is actually Newtonian gravity, Newtonian physics. We don't have to even get into Einstein so much with calculating these kinds of things out. When we are looking at these, we can use our spectral analysis. Remember, sometimes the lights are coming towards us, sometimes they're going away from us with our red shifts and blue shifts. Blue shift coming towards us, red shift going away from us. As things are going around each other, we can measure the Doppler shifts and see what's happening there. And sometimes we might have these lines merging, which will give us a sort of lineup of what's happening with the stars along the way. We can also calculate the radial velocities of things. So as they're sort of going around each other, they might be going around each other towards us, or they might be going around each other away from us, or sort of off into a different angle. So we can calculate those things out too. I'm not going to make you do it, but we just be aware that we can do that. One of the things is, as we've gotten better and better at our various technologies, we have been able to see more and more that's out there, and brown dwarfs are something that have really come into view within the past quarter century to a little bit longer than that, as we've gotten into really good infrared observations. If you sort of look at the Orion Nebula here, and we'll look at that in a number of different ways throughout our course, look at all these dots that are here. Those are not really visible to the naked eye. The thing that's in the center here, because they are warm and thus they have infrared luminosity, but they're not putting out light in Roy G. Biv. But look how many of them there are. This is a stellar nursery. It is putting out some really major stars here in the middle of the crib, but we can see a couple of other major stars. We can see some lower energy and higher energy areas of the nebula, but we had no idea until we got really into infrared astronomy just how much stuff is out there along the way. And before I let you go, I'm going to show you a book that is devoted to one of our really major advances into infrared. Here again, when we're looking at different images of the Orion Nebula, looking at it with the Hubble, we call this area inside in the middle the trapezium star cluster. It's sort of the crib of the nursery. When we look at this view here, this was in infrared light, so we can sort of see through the gas and dust. So we can see the main stars that are right here in the middle in white dramatic relief, but we're also beginning to see a lot more of the other stars that are here that seem to disappear in the clouds. When we're looking at it through infrared, we can see quite a bit more that's out there. When we are looking at the mass-luminosity relationship, again, if we sort of post how massive things are versus how luminous they are, we get a big cluster here sort of in the middle. By the time we're getting down here to 10% of the size of the sun, the engine doesn't kick on. By the time we're up here in the mega star size, there aren't that many of them. These three it mentions are actually white dwarfs. So those are actually stellar corpses or zombies. So we could actually leave those off this chart if we're just talking about main sequence stars. Main sequence star, again, hydrogen is turning into helium inside. And we'll talk a little bit more about the engines as we're talking about the life cycle of stars in a chapter or two coming up. Sometimes we get lucky and we see the binary star system edge on. So sometimes one of the stars goes in front of the other star. That happens on our planet when we're dealing with eclipses. The moon gets right in front of the sun, or the Earth gets right in front of the moon and it casts a shadow. Well, we're not talking about shadows here because these are luminous objects. They're putting light out. But if I have a 100-watt bulb and a 40-watt bulb, and the 40-watt bulb goes in front of the 100-watt bulb, it's actually going to obscure part of the light coming off the 100-watt bulb. And then when it's over here on this side, we're getting 140. Then when it goes behind, we're not seeing the 40 anymore, but we're seeing the 100. Then when it comes out over here, we've got the 100 and the 40 again. So what we're going to see is when it goes behind, we only have the 100. We have 140 up here. When we're looking at this, we're blocking out part of the 100, but we're keeping all of the 40. So we have a double dip in the light that's coming off of it, but the dips are different in their intensity, because one of them is blocking the other star completely and the other one is not. So that's part of how we can confirm an edge on eclipsing binary. And we call that, when it goes in front, a transit. When it goes behind, we call that an eclipse. So this is a transit and eclipse method. Here's another way in which we can graphically illustrate that. See, all the light from A and B is here. We've got all the light from B, but part of A is obscured. All the light from A and B again here. And here we only have A because B is completely obscured. So again, we get the double dip, but of different sizes. If the dip were in fact the same size, that might indicate more of a planet rather than a binary star system. Because the thing is, if this were a planet, there would be no light on this side, because planets don't emit their own light like stars do. And in fact, it's not just sort of boom, up and down. As one star is going in front of the other, we get this slide down to the curve and then slide back up, because it only covers part. Now it's all, and now part over to stage 4 here. So it's not just that we have it going down and up, we also have the sort of slide down across the slide up. And that will happen again on the reverse when it's going behind in eclipsing. Now, sometimes binary stars can be close enough to each other that they affect each other physically, not just gravitationally, but in terms of the material going from one to the other. And this can change the life cycle of the star. Algol. Now here, I'm going to tell you a little bit of a story for a moment, so bear with me, if you will. Notice this is Al, Algol. Well, remember I talked a little bit about a guy named Hipparchus I think in chapter 1, when we're talking about the earliest of people who would look for stars and catalog stars. Hipparchus was one of the Greeks. The Greek material pretty much disappeared from a lot of the European areas after the fall of the Roman Empire, but was preserved in very great portion by the Muslim Empire, which had grown into a golden age. They had universities, they had research areas, they had major libraries, and a lot of the Greek material that survives to us today actually comes from them. And the Muslims at that time became very great astronomers, observational astronomers. And there was a practical reason for this. Think about being a Muslim for a moment. One of the things you are expected to do is pray every day. One of the things you're expected to do when you're praying is face Mecca. Well, if you're sort of in the Middle East, you can pretty much figure out where Mecca is by just sort of knowing your geography. But if you're over in Egypt, or you're over in Libya, or if you're over in Spain, or you're up in Turkey, or you're over in Indonesia, actually the most populous Muslim country in the world, is actually not even in the Middle East now. It's Indonesia. Not a lot of people realize that. How do you figure out where Mecca is? One of the key ways in which you can do that is figure out what stars would be overhead for Mecca, and then orient yourself towards those stars. And so the Muslim catalogs for what stars were in the sky and where they were became rather good, and we preserved a lot of those into then medieval European astronomy and later. One of the leftovers of that is sometimes we have names that come from that time period. Any star that has AL as the beginning, you can bet is going to have come from that time. Aldebaran, Algol. We even have an echo of that in Star Wars, Alderaan. So we use that from there. Algebra, yeah, that comes from that time too, and we're using Arabic numbers, which technically are Hindu numbers, but never mind. And Betelgeuse is actually also a derivative of that. We still are using those names. So end of story. You can do some research on that. That would not actually make a bad final project if you wanted to do that. But Algol is a double system. One star was larger than the other. Remember from what we've already studied, larger stars burn themselves out faster. As it was burning itself out here, one of the things that happens, we'll see a little bit later in more detail, it expands out. As it expanded out, it got so close to its smaller companion, that smaller companion began to leach material off of it. We call this mass transfer. Its mass is being pulled off. And as that gets pulled off into the other star, because how bright a star is, how hot a star is in the main sequence depends upon how much mass it is. It went from being a little red to a yellow to a big white star. And this is where we are today. We have the bigger star literally being sort of almost like a vampire, the smaller star leeching off of the big star here. So it is literally changing its life cycle, whereas this red star here might have lasted 1 trillion years. It's going to burn big and bright, but it's going to burn for a lot less time there in that one here. So now the companion star becomes more massive. Our universe is great at recycling, and this is one of the ways in which it recycles. One of the ways in which we can also tell binaries is from the spectroscopic information that we get off of the light that's coming there. Again, if things are coming towards us, notice the lines are more in the blue area. If things are going away, they're more shifted towards the red. So B here is moving away from Earth, so lines are shifting towards the red of Roy G. Biv. As it's coming towards the Earth, it's shifting more towards the blue. So if we're taking readings off of the stars and we notice this shift that's taking place here, we can say, aha, then that we might not even be able to see it with the naked eye, but we can see what's going on there. You will hear over and over again through the course of this class, and if you do any further work in astronomy, something called the HR diagram. In our sense, that's not human resources or human relations. That's Hertzsprung and Russell. And they put together a big diagram based on the spectral classes, temperatures, and luminosities and masses of the stars. There are several different ways in which we can tell what a star is simply by looking at where it goes on the HR diagram. So I'm going to show you a little bit more about the HR diagram here. We have luminosity on the left-hand side here, going from dimmer at the bottom to brighter at the top. We have our spectral classes. Remember, our O-type stars are the hottest, our M-type stars are the dimmest. We can put our surface temperature across the way like this as well. We see for main sequence stars, again, main sequence means hydrogen is burning into helium. It's being fused into helium. I use the word burn, I don't mean that in a chemical sense, but that's typically how we tend to speak in astronomy. Here, any star that's on this portion, it can be an O star, it can be an F or G star, our sun would be around in here. It can be an M star, Proxima Centauri is going to be down here. All of these are turning hydrogen into helium. And the key difference there is how much mass they have along the way. But this is the Hertzsprung-Russell diagram here. You can see again, luminosity goes up and temperature goes up here. An O star is going to be big, bright, and hot up here. An M star is going to be cool and dim and small down here. So we have smaller sizes in this corner. We have bigger sizes up here in this corner. We have actually, though, our biggest sizes in terms of volume up in this corner here. These are stars up in this range here that have gone off the main sequence. When they begin to burn themselves out, they end up in this range up here for a while. Notice Betelgeuse up here, much, much larger than the sun, but cooler on the surface than the sun. It's also larger than some of our other big stars over here, including Rigel. But again, it is cooler. It's on its way out. Rigel is sort of on its way out as well. If it's off the main sequence, that means that things that are happening in here are not just simply hydrogen into helium, but helium into carbon and carbon into oxygen and on and on and on and on. And we'll talk again more specifically about that later along the way. So we can actually chart, we can generate different charts simply by putting in the different stars' luminosities and their temperatures, and it would be up here. Here's Sirius, our brightest star at night. Here's our sun. Alpha Centauri is here. Spica, that big, big star in our chart a little bit earlier. Sirius is actually a double star as well. So Sirius has a big, bright star, twice the size of the sun in terms of mass. But it has Sirius B, notice it's over here, it's actually a white dwarf. It's a leftover core of a star. And then we have Betelgeuse, which is called a red giant. It's actually a supergiant that's up there. These are all the main sequence stars. Again, notice lifetime, if you're down here, will last a lot longer than a lifetime up here. Lower mass means longer life, higher mass means shorter life. Also notice the color, notice the temperature, notice the luminosity. It's all sort of going up and in this left direction here. So pretty much once a star forms, unless it's got that algal thing going where it's doing a mass transfer, once it forms, it stays on this main sequence as long as hydrogen is turning into helium. And then once that ceases to be, we get off the main sequence here. These are regular stars here. These are dwarf stars here. These are giants up here. So as we are looking at this, again, big stars up here, smaller stars down here. We have very small radius, but we might have a very hot thing. This is where white dwarfs end up down here. This is the zombie zone in the small radius there. So we can do classifications. Main sequence is always going to be a V for 5. So our sun is a G-type star. It's also a V. It's also a 5. It's a main sequence star. Sirius is also a main sequence star. That's what that 5 there means. Proxima Centauri is also a main sequence star. Betelgeuse is not. It's a supergiant. Betelgeuse ends up in this territory here. It is not turning hydrogen into helium. It's way up in this area here. We've also got Antares and Aldebaran. Remember Al there. We've got Polaris. Polaris is actually off the chart as well. Polaris is also in its process of being on the way out. When we look at this, again, we can tell the temperature on the bottom here. We can tell the spectral type, OBAFGKM. We can tell the radius because larger and smaller. We can tell the color right away. We can tell the luminosity. So there are several key things. If we just know exactly where on the HR diagram it is, we can tell about the star. All of these, main sequence, again, turning hydrogen into helium. The only key difference in these stars that makes a difference in terms of where it lies on this chart is how much mass there is. There's no blue dye that we put over here and red dye that we put over here. It's all dependent upon how massive the stars are. And that determines the color, that determines the temperature, that determines the life sequence, that determines the size. Everything is dependent upon that. So lower mass down here, higher mass up at the top along the way. So it's the mass. It's all about the mass. When we are comparing ourselves to a supergiant, VY Canis Majoris, that's in the constellation of the big dog, Canis Major. So this is in the vicinity in the sky of Sirius, that bright star there. This is one of the largest stars known. I think at some points it has been classified as the largest star known. Notice how tiny, 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 tiny the sun is compared to this. In fact, this whole little circle here is the orbit of the Earth around the sun, not just the sun itself, but the orbit of the Earth around the sun. And this is super massive and huge, but it's also not going to last very long because by the time you get this big, you burn yourself out really quickly. I think I already mentioned it, I'm going to put up a video that shows you size comparisons, and it starts in the solar system and then goes larger and larger along the way. When we are looking at Sirius, again, our main star in Canis Major, Sirius A is the big star, Sirius B is the smaller star that is going around it along the way, and we have it being exposed here by the Chandra X-ray telescope. So this has been modified because we can't actually see the X-rays. But one of the things that it shows us is that we have our really, really faint star that we're seeing in this image brighter in X-rays than it is in regular sort of Roy G. Biv visible light along the way. So we will talk about all of those things a bit more later. And let me stop the sharing here and let me see if I can pause this. If this just keeps running, then I apologize, but I'm going to run and get a book and I'll be right back. Okay, let's see if that worked here. You'll notice the background has changed, it has shifted, and I'm probably blending in because of the shirt that I'm wearing to the image here. Let me see if I can get well out of the way for you here. This is actually an image of the Spitzer Space Telescope that just went offline earlier this year. And here's a book I would like to recommend, More Things in the Heavens, How Infrared Astronomy is Expanding Our View of the Universe. And this was written just before the Spitzer telescope went offline. But the Spitzer telescope was supposed to be up for about 2.5 to 5 years. In the end, it lasted for almost 17 years, which is one of the interesting things about NASA and the work that they do, is that when they get it right, they get it really, really right. The Hubble, for example, was supposed to last maybe 10 years, and we're celebrating the 30th anniversary today. The thing about the Spitzer is it is an infrared, it was an infrared telescope. It's actually, I believe, still up there. It's just not functioning anymore. But it's probably done as much, if not more, for our understanding of the way the universe is than even the Hubble, because we have to get past the atmosphere to get almost anything of reliability in infrared in a true sense. We can adjust and modify and stuff like that. But the other side of this is it had a primary mission because it had to super cool everything on the telescope so that it could pick up the most distant of faint heat kinds of sources. When the coolant ran out, it had to do other kinds of gymnastics to keep itself from heating up in the sun so that it couldn't function anymore. And it was really ingenious in the way that NASA engineers were able to figure that out and extend its life by more than a decade after that work. But this book has various chapters in it. Let me come here rather quickly to see. It talks about, in chapter 3, the birth of stars and planetary systems. See, that's going to be useful for us, so I'll probably refer to this book a couple more times in our stuff that goes along here. The Milky Way and interstellar matter. Well, we're going to be talking about that here coming up very quickly in another lecture. just beyond the Milky Way, meet the Milky Way's neighbors, polling the universe, active galactic nuclei and quasars, galactic clusters. This is the book. This is the book on the telescope that has perhaps the most to do with what we're studying in our class today. This is one of the great observatories. There was a series called the NASA Great Observatories, and the Spitzer was one of them. The Chandra X-ray, which also has a lot that will, especially when we get out into funkier things in the universe, was also one of those, and the Hubble was also one of those. So we have a really good system of looking at the different parts of our spectrum that won't get through our atmosphere. X-rays tend to not, gamma rays tend to not, infrared is often blocked, even Roy G. Biv gets distorted along the way. So we have quite a number of things that are useful, and I wanted to highlight this book. This book I got, it's very nice hardback. I love hardback books because I tend to use them. This is one of those books that probably for astronomy will be well worth whatever you pay for it, because it's not going to be outdated next year. It's not going to be outdated 2 or 3 or 4 years from now. This is talking about pretty much the complete mission of the Spitzer. And even though we'll make advances beyond that, this will be a good thing for at least the next 10 years. And I got this used on Amazon. You can look for it used as well. I think new, it's probably about $35 or $40. I think I managed to get this for $20 along the way. That's actually one of the books that I got on interlibrary loan, because when they're $40, $50, you never know, do I really want this book? I got it on interlibrary loan. I read it. I almost couldn't put it down as I was reading it. I said, nope, I've got to buy this one, and I did, and I did. So I can highly recommend that book to you. As a book. It does not go into great mathematical detail, which I think is a great saving grace, because there's a lot of math in astronomy, especially when we're talking about different things like what we're talking about. But to get a good concept of what's going on, you don't always need all of that. And what you can do if you're a mathematical astronomer, astrophysicist, or want to go beyond that, this is a good launching point. This book is a good launching point. This course is a good launching point. And one of the things that I have found in my career is that I like to get into the depths and the details of a lot of those things, but at the same time, I like the surveys and to look at the broader perspectives of the universe. There are people who devote themselves entirely to infrared astronomy. There are people who devote themselves entirely to infrared technology for astronomers. There are people who specialize. I'm not a specialist in that regard. If I had a specialty, it would be in the history of astronomy. But that's one of the reasons why I love teaching courses like this one, and I love books like that. So I will see you in our next lectures.